Good morning, dear friends. I hope you all are doing great. Do stay in a pink of health. Let us start today's lesson, which is biomolecules. So, previous class we have discussed about the structure of glucose molecule. We told you that the glucose molecule has basically a particular structure, like all the carbon atoms are arranged in the glucose molecule in a straight chain. Okay. Second thing which I discussed with you was the glucose molecule had a aldehyde group, CHO group. Third thing is that glucose molecule has one primary OH group. That sixth carbon is having the primary OH group. And we also discussed that the glucose molecule has 5 OH groups in total. And those 5 OH groups are basically 4 are secondary OH groups and 1 is primary OH group. Apart from that, let's understand today the limitations. Okay? Let us see the limitations of the open chain structure of glucose, which we have discussed it previous time. If you take the open chain structure of a glucose molecule, you will find out that it does not show, or rather it does not give this test. When glucose molecule interacts with 2,4-dinitrophenylhydrazine, okay, this reaction does not click. That means there is no reaction between glucose and 2,4-dinitrophenylhydrazine. Okay, what is the reason that why don't glucose react with 2,4-dinitrophenylhydrazine? Remember one thing, 2,4-dinitrophenylhydrazine reacts with aldehyde. And last time I showed you that glucose has free aldehyde group. When you see the open chain structure of glucose, it has a free aldehyde group. So this guy should react with glucose, but it does not react. What will be the reason? The reason is that the open chain structure changes into the cyclic structure. Cyclization happens. When open chain structure of glucose changes into the cyclic structure, then it does not have free aldehyde group. When it does not have free aldehyde group in cyclic form, it fails to react with 2,4-dinitrophenylhydrazine. And in the same way, it fails to give the Skiff's base test. And also does not give addition product. It does not react with sodium bisulfite. So my dear friends, if we talk about the open chain structure of glucose, it has a free aldehyde group. It should react with 2,4-dinitrophenylhydrazine. It should give the Skiff's base test. It should also interact with sodium bisulfite. But it doesn't react. So what will be the reason? The reason is quite simple. That is, the open chain structure of glucose changes into the cyclic structure. So when open structure changes into the cyclic structure, it has no free aldehyde in cyclic structure. Okay? And it doesn't react with these. So it's a limitation. So it's a limitation of open chain structure of glucose. Okay? When somebody asks you a question that why doesn't glucose give 2,4-dinitrophenylhydrazine test, Skiff's base test, or it doesn't react with sodium bisulfite? The answer is that the open chain structure changes into the cyclic structure, and that cyclic structure does not have free aldehyde. That's why it does not react. So my dear friends, it's a limitation of open chain structure, because open chain structure does not react with them, because open chain structure changes into cyclic structure. Remember, I am repeating, it changes into cyclic structure. Now second limitation. If we talk of pentaacetate of glucose, yesterday I have made pentaacetate of glucose. How? I took a glucose molecule, I made it to react with acetic anhydride, and I got glucose pentaacetate. Okay? Now this glucose pentaacetate does have a free aldehyde group. Okay? If you see the structure of glucose pentaacetate, you will find out it has a free aldehyde group, and it should react with hydroxyl amine to give me oxime. But it doesn't happen. What is the reason? Again, the same thing happens. Open chain structure of glucose which has a free aldehyde group, okay? Open chain structure changes into the cyclic structure, and the free aldehyde group does not exist when open chain of glucose changes into the cyclic structure. That means pentaacetate of glucose will not react with hydroxyl amine to form oxime. Now, I will explain these terms one by one, but let us see here the last point. Glucose exists into two anomeric forms. So these anomeric forms we will discuss later in this chapter. These are basically isomeric forms of glucose. And what are those? You have alpha D glucose and beta D glucose. These alpha D glucose and beta D glucose are cyclic forms of glucose. So it's a limitation of open chain structure. They are not open chain structures of glucose, they are cyclic forms of glucose. These anomeric forms are cyclic forms of glucose. But our topic was open chain structure. So when we talk of open chain structure of glucose, it gives me no idea about alpha D glucose and beta D glucose, which are the anomeric forms of glucose. Anomeric forms, basically isomeric forms of glucose, which we will discuss later in this chapter. Okay? These anomeric forms are cyclic forms of glucose. Okay? So this is one more limitation, because this third terminology tells me that glucose exists into two cyclic forms. So it's a limitation of open chain structure. We say that glucose exists into this open form, but in actual sense it exists into alpha and beta form here. And these, remember, this alpha and beta form are the crystalline forms of glucose, and they are optically active. Alpha and beta forms are crystalline forms of glucose. They are optically active, and both of them can rotate the light in clockwise direction. But their optical activity will be different. Okay? And they also do have a different melting points. We will be discussing about this anomeric form later, as I told you. So let us discuss these points first. Let me give you a little idea about how does it work. See here, you have a glucose molecule with you. So 1, 2, 3, 4, 5 and 6 CH2OH. Third carbon has OH group on left side, which I have told you. This aldehyde group is free. So this is free aldehyde group, free aldehyde or aldehyde group. So my dear friends, this guy should react with 2,4-dinitrophenylhydrazine. Okay? aldehyde will react with this molecule. So this reaction should be possible because 2,4-dinitrophenylhydrazine. I will write down 2,4-dinitrophenylhydrazine. Okay. Even I can draw the structure, which is not important here. We can discuss about it later, but still for you people, I will draw the structure. So 2-nitro, 4-nitro, we have 2,4-dinitrophenylhydrazine. So this guy is our hydrazine. This is 2 and this is 4. This is 1, 2, 3 and 4, 5 and 6. 2,4-dinitro, this is phenyl, and this group is hydrazine. Free aldehyde group, remember, free aldehyde will always react with 2,4-dinitrophenylhydrazine. It should react. But this is the open structure of glucose. In my first limitation, I told you that this glucose does not react. But here I am telling you it should react. Because aldehyde is here, it should interact with this aldehyde. Because these two hydrogens, if I show you, these two hydrogens and this oxygen should come out. So reaction is possible. Reaction is possible. But I am saying that it does not react. What is the reason? The reason is simple. I will show you. Because that cyclic structure we are dealing with later. But for you people, I will draw one cyclic structure here so that you can understand. O will be removed from here, H2 will be removed from here, so reaction is possible if the glucose molecule has free aldehyde group. But in limitation, I am telling that it does not react. But here I am saying it reacts. But actual thing is that it does not react. How? Because this open structure will change into the cyclic structure. Which structure? Cyclic. When open chain structure changes into the cyclic structure. Have a look. So you have a cyclic structure of glucose here with you. This structure you will learn later, but I am drawing it for you people to make you understand. OH, H, H, OH, H, and finally CH2OH. Now look here, this is your first carbon, 2, 3, 4, 5. And let me tell you, this first carbon, in open structure if you see, open structure of glucose if you see, first carbon is aldehyde. First carbon is aldehyde in open structure. And it should react with 2,4-dinitrophenylhydrazine. But actually, this open structure of glucose is converted basically into which structure? Cyclic structure of glucose. Cyclic structure of glucose. And that's why this guy will fail to react with this thing. Now it will not react. So remember, open chain structure of glucose can react with this, but it does not react. Why? Because the open chain structure of glucose is converted into cyclic structure, and this cyclic structure has first carbon, which we will discuss later. It's known as hemiacetal carbon. Hemiacetal carbon. There is no free aldehyde. You can see here, there is no free aldehyde. So when it does not have free aldehyde, will it react with this thing? No, it will not react with this thing. No reaction at all. So once again, open structure, why does it fail to react with 2,4-dinitrophenylhydrazine? The reason is simple. The reason is that open chain structure actually changes into the cyclic structure, and in cyclic structure the first carbon is hemiacetal carbon, which does not have a free aldehyde group, so it fails to react with this particular molecule, which is nothing but it is your 2,4-dinitrophenylhydrazine, because this oxygen is not available now. if I remove 2 hydrogens but oxygen is not available. Okay? So that was the first point. Second point is the same thing. If I treat it with Skiff's base, first of all, open structure will change into cyclic, then cyclic structure will not react with the Skiff's base. Okay? If I make it to interact with sodium bisulfite, there is no reaction. Reason is that this guy does not have free aldehyde group. Cyclic structure of glucose does not have free aldehyde group. I hope, my dear friends, you have understood. So let us take on the second point was there that can be understood by the same process. You know what was that? I told you that glucose pentaacetate also does not react with hydroxyl amine to form oxime. What is the reason? Reason is again that glucose pentaacetate will not be in the open form, it will change into the cyclic form. Cyclic form has no free aldehyde, it will not react with the hydroxyl amine. And the last point which we discussed was, we say that glucose has an open structure, but in actual it exists into 2 crystalline forms, alpha D glucose and beta D glucose, with different melting points, okay, with different optical activities like degree of rotation. Okay, now this was all about the limitations. I hope you have understood, and we will further discuss about those anomeric forms, optical activities in this particular chapter. Please make note of that particular thing. So my dear friends, let's talk about the capital D and capital L configuration in carbohydrates. See here, most of the students do get confused when they try to differentiate between capital D and small d. Okay, small d is also represented by a positive sign. When you have capital L and you have a small l, and here we have a minus sign with us. Cool? What is the meaning? If you look at this capital D, it is just a configuration, arrangement. Arrangement of what? Arrangement of OH group. Arrangement of OH group on the right side of last chiral carbon. Okay? If the OH group is present on the right side of last chiral carbon in a carbohydrate, we call it as capital D configuration. If the same OH group on last chiral carbon is present on the left side, we call it as capital L configuration. So it's an arrangement of OH group on last chiral carbon in a carbohydrate, which gives me capital D and capital L. But my dear friends, when you look at small d and small l, you will find out that the D is also represented by plus and small l is represented by minus. This gives me optical rotation. So this D and L, they are for configuration, arrangement related, and this is related to optical activity. Now my dear friends, my topic is here D and L configuration. But before understanding D and L configuration, let us understand a term called as chirality. Chirality. So what is this chirality all about? We will have a look. First of all, I will tell you, if a carbon atom, mostly because in carbohydrates we will be dealing with the carbon atom, if a particular atom is surrounded by 4 different groups, okay, we call it as chiral center. Have a look. Let us suppose I have a carbon with me. This carbon is surrounded by, let us suppose, COH group, H, OH and CH3. Now have a look at this carbon. This carbon is surrounded by 4 different groups. We call it as chiral carbon. What are 4 different groups? OH, carboxylic acid, hydrogen and CH3. Let me call it as A, B, C and D. So this carbon, I'll put a star here. This carbon can be called as chiral carbon. So before defining what chirality is all about, let us see what is this chiral carbon all about. Okay. So what is chiral carbon? This guy is our chiral carbon. So what is it? Carbon surrounded by 4 different groups. Okay. Now why I am looking at chiral carbon? What is the point? See, I am telling you that this is a chiral carbon because it is surrounded by 4 different groups. Clear? But what is the need? The need is very much important here. That is, if any molecule has a chiral center or chiral carbon, it is optically active. If any molecule has a chiral center, it is optically active. So I will write down my second point. A molecule having a chiral carbon is optically active. So what does it mean? That means this molecule is optically active. You know which molecule is this? This is actually our lactic acid. Lactic acid has 1 chiral carbon. Now you will be thinking, what about this carbon and this? They are not chiral carbons. You can open up the structures here. Have a look. C double bond O, OH. And here we have OH, here H, and here we have H, H and H. Look at this carbon. This is not surrounded by 4 different groups. It is surrounded by 1, 2, 3. They are same. I can call it as A, this one also as A, this one also as A, and this group I can call it as B. So this carbon is surrounded by 3 similar groups and 1 different group, that is B. So it cannot be chiral. I told you chiral carbon means carbon surrounded by 4 different groups. Look at this carbon. This is surrounded by 3 similar groups and 1 different group. So this is not a chiral carbon. Clear? Let us take an example of now this carbon. If you take this carbon now in consideration, let me draw it once again. Look here, C double bond O, OH. Okay, the rest of the structure we have OH, H and CH3. Now look at this carbon. This carbon is surrounded by how many groups? 1, 2 and 3, like A, B and C. So this guy is also not surrounded by 4 different groups, it's surrounded by only 3 different groups. Now if you think that this C has a double bond with oxygen, I can take it 2 times also, it does not matter. Like if I can take it like this, that will be the phantom atom. But still they will be same. Okay. So this is also not a chiral carbon because this carbon is not surrounded by 4 different groups. So how many chiral centers are there? Can you tell me in this molecule lactic acid? This is not a chiral carbon. This is not a chiral carbon, but this is a chiral carbon with us. This one is a chiral carbon. And I told you a molecule having a chiral carbon is optically active. So that means lactic acid will be optically active in nature. So my dear friends, we were talking about the chirality. So have a look. Chirality is basically a property of a molecule, okay, that is not identical to its mirror image. That means a molecule, okay, who is chiral. I told you previous time that lactic acid is a chiral molecule because it has a chiral center, which is carbon. It should not be identical to its mirror image. Then I took the lactic acid here. Have a look. This is my lactic acid. And I have taken its mirror image here. So when I take its mirror image, what happens? You look at this structure. Here the OH group is on the right side and here the OH group is on the left side. That means, are they identical structures or they are exactly opposite structures? They are exactly opposite. They are not identical. So when a molecule, any molecule is said to be chiral when it is not identical to its mirror image, when it's not similar to its mirror image. Okay, let us suppose if I take this hand, okay, if I show it to the mirror, it shows exactly opposite. How? Let me show you. Let me give you the demonstration. This is my hand right out here. Have a look. And now, how I have to show it? Like this. So this is the mirror image of this. If you try to superimpose them, if you try to put them onto each other, you can have a look here that there is no superimposition. They are non-superimposable. They are non-superimposable. See here, I am showing this hand to the mirror and it shows me exactly, opposite. Don't do like this, otherwise they'll become superimposable in this way. Okay, so what you have to do? Show it exactly opposed. For example, you might have tried the selfie camera. When you are trying to have a food by your right hand, okay, when you take a click, what happens? It shows you, taking the things by left hand. Okay, so what is the meaning? The meaning is that it shows exactly opposite structure. If this is, I am showing to the mirror, this palm of my hand, I am showing to the mirror, this direction, and it will not show me exactly, it will show me like this. So when I try to superimpose them, when I try to fix them together, they won't fix up. See the thumbs, they are on in the opposite directions. So my dear friends, remember always, the molecule which is chiral will be always non-superimposable to its mirror image. So I will write down chiral molecule is non-superimposable to its mirror image. To its mirror image. Have a look here. If I take this molecule and try to fix it here, let me take this molecule and put it here. What will happen? OH will fall on H. H will come on OH. Yes or no? So that means here we will have a difference. OH will fall on H. Take this molecule, take it out, put it here. Once again, take this out and put it here. What will happen? OH will come on H. H will come over OH. That means they don't fit. When they don't fit together, understand they are the mirror image of each other. Okay? Don't think that you are showing actually molecule to the mirror. Actually, these are two different molecules and they look like mirror images. Don't think that you take one molecule and show it to the mirror. No, not like that. You are taking two molecules and they look like mirror images of each other. And that's exactly, we call them as chiral molecules. And they are optically active. Chiral molecules are optically active. So now see the optical activity. I am using a plus sign. In place of plus sign, I can also use small d. Remember, small d or plus sign. We'll discuss about it later. And here I can use small l or minus sign. This plus d, this d and this plus, it means it rotates plane polarized light, plane polarized light in clockwise direction. And what does this L or minus means? This means it rotates light in anti-clockwise direction, because these two structures are exactly opposed. It rotates light in anti-clockwise direction. And you should know that which light it is. Let me write down here. It rotates PPL. What is PPL? Plane polarized light, unidirectional light in anti-clockwise direction. That means L. It also means, L also stands for levorotatory, and D also stands for dextrorotatory. So D is dextrorotatory, L is levorotatory. We will discuss about these things later. Okay? Our actual topic is basically capital D and capital L configuration. So these things will also come later. But first of all, if you take a molecule, lactic acid, which is positive. Now you will tell me that where from this plus sign has come. These are experimental, determinations. It's not, you can't look at a molecule and tell that it will rotate light clockwise or it will rotate light anti-clockwise. You have to perform an experiment through which you can tell whether it will rotate light clockwise or anti-clockwise. Because previous time I told you something. What was that? Have a look. I told you, roughly I'm just telling you in a very brief way. I took light. Okay? Which light was that? Plane polarized light, PPL, plane polarized light. And I took a solution. I took a carbohydrate solution. We call it as a sample tube containing carbohydrate solution. When this PPL, plane polarized light, is passing through this particular solution, I am passing it through. So this is your light, unidirectional. What happens? There are two possibilities which can happen here. What are those two possibilities? Let us see. The two possibilities are like this. The light may be rotated either clockwise. This is the actual, oscillating, plane of the light, but it has been bent now. Okay? Or light can be rotated anti-clockwise. Okay? So there are two possibilities. Clockwise or anti-clockwise rotation of a light. So when we take on PPL, plane polarized light, okay, and make it pass through a carbohydrate solution, there are two possibilities. The light can be rotated either clockwise or anti-clockwise. Okay? For example, if I am observing, I am an observer, I am observing what is happening to the light here. If this light is actually turning in this direction, then I will tell, if I am looking, see the light is here and it has bent in this direction. I am the observer, I will look at the light and I will see it has bent right, so clockwise. If I look at this light and I will see, it has bent left, so anti-clockwise. So that means this will be your D and this will be your L. This will be plus and this will be minus. But depending on carbohydrate. If in place of this carbohydrate, if I place this molecule plus lactic acid, then what will happen? Light will be only rotated clockwise. If I place this mirror image, this one, here in this solution, then the light will be rotated anti-clockwise. That means it depends on the nature of a molecule. Okay? And now you have plus lactic acid and minus lactic acid. It rotates the light, plane polarized light in clockwise direction. It rotates the plane polarized light in anti-clockwise direction. It's represented by plus, it's represented by minus, it's represented by small d, it's represented by small l, and both these optically active optically active substances are called as enantiomers. So what are enantiomers? Enantiomers are basically the molecules, okay, chiral molecules, which have same molecular formula. Molecular formula of enantiomers is same. Chemical properties are also same, but their optical activity is different. One is rotating the light in clockwise direction, another one is rotating the light in anti-clockwise direction. So once again, what are enantiomers? What are enantiomers? Molecules, chiral molecules. Okay, those chiral molecules which are basically mirror images of each other. They are mirror images of each other, means exactly opposite, non-identical, non-superimposable mirror images with same chemical properties. Chemical properties will be same because functional groups are same, but their optical properties are different. One rotates the light clockwise, another one rotates the light anti-clockwise. One is dextro-rotatory and another one is levo-rotatory. I hope, my dear friends, you have understood this particular thing. Okay? After understanding these certain small things here, let us come back to our topic. What are those? Capital D and capital L. What does this capital L and capital D stand for? So we'll talk about this now. So let us come to our topic now, which is here. And I taught you some basics before dealing with this particular thing. Okay? Now what is D? Configuration. D configuration. Okay? It means, it indicates the presence of OH group on the right side of last chiral carbon in a carbohydrate. If you take a carbohydrate, okay, if you find out that the OH group is present on the right side of the last chiral carbon, okay, it will be your D configuration. And for your kind information, remember, all natural sugars have D configuration. So my dear friends, all natural sugars will have D configuration, means they will be D sugars, capital D sugars. It's not dextro. Small d is dextro, positive sign is also dextro, but capital D means presence of OH group on the last chiral carbon on the right side. Let's have a look. Let's take our molecule here, glucose molecule. And let me tell you how many chiral carbons are there. I showed you that this CHO cannot be chiral. Have a look. It has 3 groups only, 1, 2 and this one, that is 3. So it's not chiral. Chiral will start from the second, third, fourth, fifth, and finally you have CH2OH. If you open up this CH2OH also, have a look here, H and H. Look, 2 similar groups are here. A, then B, and this entire thing will be C. But this carbon contains 2 similar groups, so it cannot have 4 different groups now. If this is A, this is also A, this is B, and this entire part is C. That means this can also not be a chiral carbon. So remember, the first carbon and 6th carbon, they are not chiral. This and this, first and 6th. But look here, the second carbon, what is here? OH, H. Look here, this is A, okay? This is B, alcohol, aldehyde, hydrogen, A, B, C. And then this entire part is D. That means the second carbon is surrounded by 4 different groups. OH, aldehyde, H, and this entire part. This entire part like this, I will show you. This entire part. A, B, C and D. So this is our chiral carbon. I'll put a star here. Now I'll go a little faster. Third carbon is also chiral carbon. Which group is here? OH is A, H is B. Okay. Then this part is C. Have a look. This part is C. This is A. Let's suppose this is B. This is C. And this part will be D. So it is surrounded by 4 different groups. Third carbon is surrounded by A, B, C and D. So this guy is also a chiral carbon. So I'll put a star here, chiral carbon. So now after this OH, H. Okay, this is the 4th carbon. This is also chiral carbon. Have a look. A, B. Then this entire part is C and this part is D. Clear? So this is also chiral. 5th carbon. OH, H. Let's suppose this is A. This guy is B. This guy is C. And this entire part is D. That means this guy is also chiral carbon. So except 6th carbon and 1st carbon. How many chiral carbons are here? 4. 2, 3, 4 and 5. So N stands for number of chiral carbons. Tell me how many chiral carbons are here? So N is equal to 4. So our glucose molecule has 4 chiral carbons. How many? 4 chiral carbons. So will it be optically active or inactive? Experimentally it has been found that it's optically active. Clear? And it has also been determined because it has chiral carbon. First thing, glucose has 4 chiral carbons. So we think when it has chiral carbons it will be optically active. It can rotate the light clockwise or anti-clockwise. And what we found that it is rotating the light clockwise through experiment. Okay, we passed on the plain polarized light through the solution of glucose. We found that it's rotating the light in clockwise direction. So I will write down here for the glucose molecule. Look here my dear friends, try to understand. I will write down plus glucose. What is the meaning of plus glucose? That means experimentally it has been found that glucose can rotate the light in clockwise direction. So plus glucose. In place of plus, you can write down also D, small d. Small d also means dexterous clockwise rotation of light. But our topic is D configuration. What is the meaning of D? This capital D. Okay? This plus sign basically means actually small d. But we have to talk about capital D. Capital D means how many chiral carbons are here in this? 1, 2, 3 and 4 chiral carbons. And which one is the last chiral carbon? The 5th carbon. Because 6th is not chiral, 5th is chiral. So 5th is known as here last chiral carbon. Last chiral carbon. Okay? Now 5th carbon is our last chiral carbon. Okay? What is the OH group on the last chiral carbon? Look here at OH group. OH group is on right side of last chiral carbon. So OH group is on right side of last chiral carbon. Have a look. The presence of OH group on the right side of last chiral carbon in a carbohydrate. Who is your carbohydrate? Glucose. What is the optical activity of glucose? Plus. Plus means dextrorotatory. It can rotate the light in clockwise direction. But is it a capital D configuration or does it have capital L configuration? Remember, all natural sugars will have D configuration. But what is the meaning of D? D stands for that OH group should be present on the right side of last chiral carbon. Who is the last chiral carbon in glucose molecule? 5th carbon. Where is the OH group? OH group is on the right side. So now tell me my dear friends, when the OH group is present on the right side of last chiral carbon, is it a D configuration, capital D? or capital L? It is capital D. So I will write down here D. Capital D. So it's here D plus glucose. There are other terms also like alpha, beta. You'll be thinking like alpha, D plus glucopyranose. Those terms can be explained later. But how much we have read, I am explaining only that much, how much we have read here. Is it clear? So have a look. This is your D plus glucose. D stands for the presence of OH group on the right side of last chiral carbon. This positive sign means through experiment it has been found that the glucose can rotate the light in clockwise direction. Clear? So plus. In place of plus you can also write down small d. See the difference between this and this. This is for rotation, optical activity, and this is just arrangement of OH group on the right side of last chiral carbon. Then you have a glucose molecule. So D plus glucose you have. Tell me how many chiral carbons are there in glucose molecule? 4. It's optically active. Okay? Let's come to the another point here. That is L configuration. L configuration. Let's talk about L configuration. Obviously, my dear friends, this capital L stands for exactly what? Opposite. And remember, L stands for actually the presence of OH group on the left side of last chiral carbon. But remember, all sugars are D sugars. All natural sugars are D sugars. So L sugars are, not natural, but you can synthesize them in laboratory. Okay? Let's have a look. It indicates the presence of OH group on left side of last chiral carbon. Please remember, all sugars, all natural sugars are D sugars, capital D. But what about L sugar? L sugar does not exist in nature, but you can synthesize it in laboratory. So how can I explain you what is L sugar? Let us take the mirror image of D sugar. The mirror image of D sugar will be exactly what? The L sugar. Have a look. Two, three, four, 5. Okay? OH, 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 CH2OH, H, H, H and H. We know that second carbon is chiral, third is chiral, fourth is chiral and fifth is chiral. First and the last, sixth, they are not chiral. So second, third, fourth and fifth. Where is this is the last chiral carbon I will show you here. It's last chiral carbon. What was this molecule all about? I discussed already. This is capital D. Capital D stands for the presence of OH group on right side of last chiral carbon. Last chiral carbon is 5. On right side is OH group, so it's capital D. Experimentally, it has been found that it can rotate the light in clockwise direction, so plus. And we know that it's a glucose molecule, so I will write down glucose. Let me take the mirror image of this. If I take mirror image of this, so I will get an enantiomer, as I discussed. I will get an enantiomer of this, which has, enantiomer will have optical activity exactly opposite to that of this particular molecule. Have a look. CHO. Let me write down a little bit here. So I will get some space. CHO. OH will go on right side and here it will be on left side. Okay, it's on left, here it will be on right side. So here it's on left. Here also on left side. exactly opposite structure you will get. CH2OH. So now this is chiral carbon, chiral, chiral and chiral. Now look here. This is first carbon, second, third, fourth and fifth and sixth. The fifth one is last chiral carbon. Last chiral carbon. Once again I will tell you these two are now enantiomers. And you know that enantiomers will have optical activity exactly opposite. You got my point? Okay. So enantiomers that we mentioned here, enantiomers. Okay, they have different optical activities. Let's have a look at it. Last chiral carbon is fifth chiral carbon. What is the OH group? On left side. What is the OH group here? On right side. Correct? So this is D because it has the OH group on right side of last chiral carbon. This is last chiral carbon. Where is the OH group? On left side. So it will be capital L. And I told you this structure and this structure, they are enantiomers. And enantiomers basically means their optical activity will be exactly opposite. So enantiomers will have optical activity opposite. So what is the optical activity here? Plus dextro. And what will be here? Opposite. What is the opposite of that? Opposite of plus is minus. If this is rotating the light in clockwise direction, this L form will rotate the light in anti-clockwise direction because they are enantiomers and their optical activity will be exactly opposite. This is plus, this will be minus. This is D configuration, right side OH group on last chiral carbon. This is L configuration, left side OH group on last chiral carbon. And rest of the structure will be glucose molecule. This is natural. D plus glucose is natural. It exists in nature. But this L form, you have to synthesize it in laboratory. So I hope, my dear friends, you have understood what D is, capital D is, and what capital L is. Capital D means the position of OH group on right side of last chiral carbon, and capital L means the position of OH group on left side of the last chiral carbon. D means on right side of last chiral carbon, OH group. L means OH group on the left side of last chiral carbon. My dear friends, I hope you have understood this D and L configurations, capital D, capital L. Small d and small l means plus and minus. Plus means dextro-rotatory, minus means levo-rotatory. Dextro basically means to rotate the light in clockwise direction, and levo basically means to rotate the light into anti-clockwise direction. And when I take the mirror image of any molecule which is chiral, I have a glucose molecule which was chiral. I took its mirror image. It has 4 chiral centers, 4 chiral carbons. When I took its mirror image, the optical activity will be exactly opposite. And I call these two structures as enantiomers. These two are enantiomers of each other. One is dextro-rotatory, another one is levo-rotatory. I hope you have understood. And with this, I will take the leave. I will come up with a new topic from the biomolecule chapter tomorrow. Okay, till that time, have a good day. Yo-yo.